What is the use of strings in science and what is the size of it? Strings play an important role in many areas of science, including computer science, mathematics, physics, and biology. Here are a few examples. 1. Computer science. In computer science, strings are used for a variety of purposes, such as representing text data, storing and manipulating names, addresses, and other types of information, and parsing and processing data from various sources. 2. Mathematics. In mathematics, strings are used to represent sequences of symbols or numbers, and are studied as mathematical objects in their own right. 2. For example, string theory is a theoretical framework in physics that seeks to unify the principles of quantum mechanics and general relativity. 3. Physics. In physics, strings are used to describe the behavior of particles and other physical systems. 3. For example, in string theory, particles are modeled as tiny strings that vibrate at different frequencies. 4. Biology. In biology, strings are used to represent sequences of DNA, RNA, and other biological molecules. 4. These sequences are analyzed to understand the function and evolution of different organisms, and to develop treatments for genetic diseases. The size of a string in science depends on the specific application. For example, in computational biology, strings can be millions of characters long, representing the complete DNA sequence of an organism. In cryptography, strings may be much shorter, representing encrypted messages or keys. In general, the size of a string is limited by the amount of memory available in a computer, and can be quite large. Explain strings in terms of physics. In physics, strings are often used as a model for the behavior of particles and other physical systems. The idea is that particles, rather than being point-like objects, are actually tiny, one-dimensional objects known as strings. These strings can vibrate at different frequencies, and these vibrations determine the properties of the particles they represent. This idea was first proposed in the framework of string theory, a theoretical framework in physics that seeks to unify the principles of quantum mechanics and general relativity. In string theory, strings are treated as objects that exist in a higher dimensional space-time, and the vibrations of these strings determine the properties of the particles they represent. One of the key features of strings in physics is their ability to vibrate in many different modes. Each mode corresponds to a different particle, and the different modes can be combined to produce more complex particles. This allows string theory to describe the behavior of a wide range of particles, from the basic building blocks of matter to more complex particles such as quarks and leptons. Overall, the use of strings in physics provides a new way of thinking about the behavior of particles and other physical systems. By treating particles as tiny strings, physicists can study their properties in a more abstract and mathematical way, which has led to many new insights into the behavior of the universe. What are the benefits of strings in physics? In physics, the use of strings as a model for particles and physical systems has several benefits. 1. Unification. String theory provides a unifying framework for understanding the behavior of particles and physical systems. 1. By treating particles as tiny strings, physicists can study their properties in a more abstract and mathematical way, which has led to many new insights into the behavior of the universe. 2. Consistency. String theory offers a more consistent and coherent explanation for the behavior of particles and physical systems than other models. 2. For example, string theory can explain the behavior of both quantum mechanics and general relativity, which are two fundamental theories in physics that have historically been difficult to reconcile. 3. Predictive power. By treating particles as strings, physicists can make predictions about their behavior that are not possible with other models. 3. This has led to many new insights into the behavior of particles and physical systems, and has helped to advance our understanding of the universe. 4. Explanation for dark matter and dark energy. String theory provides a possible explanation for the existence of dark matter and dark energy, two mysterious substances that make up the majority of the universe's mass-energy content. 5. Improved mathematical understanding. By treating particles as strings, physicists can use mathematical techniques and theories developed for strings to study their behavior. 5. This has led to many new insights into the behavior of particles and physical systems, and has helped to advance our mathematical understanding of the universe. Overall, the use of strings in physics provides a new and powerful framework for understanding the behavior of particles and physical systems. This has led to many new insights and advances in our understanding of the universe, and has the potential to help us unlock many mysteries about the nature of the universe. What are the drawbacks of strings in physics? While the use of strings in physics has many benefits, there are also some drawbacks to consider. 1. Lack of experimental evidence. Despite being a powerful and well-developed theoretical framework, string theory has yet to be confirmed by experimental evidence. 1. This means that string theory remains a purely theoretical framework, and its predictions and insights have yet to be verified by experimental data. 2. Complexity. String theory is a highly complex and abstract theory, and its mathematical foundations can be difficult to understand and work with. 2. This makes it challenging for many physicists to engage with string theory, and can limit its impact and reach. 3. Multiple solutions. String theory is highly flexible and allows for multiple possible solutions, which can make it difficult to determine the correct solution. 3. This can lead to confusion and uncertainty about the implications of string theory, and can limit its predictive power. 4. Lack of consensus. While string theory has a large and dedicated community of researchers, there is still a lack of consensus on many key issues within the field. 4. This can make it difficult to determine the direction of future research and to build a unified understanding of the theory. 5. Open questions. String theory still has many open questions and areas of research, and much remains to be understood about the theory and its implications. 5. This means that string theory is still a rapidly evolving field, and its impact and reach may be limited by our current understanding of the theory. Overall, the use of strings in physics is a powerful and well-developed theoretical framework, but it is also a highly abstract and complex theory that has yet to be confirmed by experimental evidence. While string theory has many benefits, it also has several drawbacks that need to be considered when evaluating its impact and reach. History of strings in terms of physics. The history of strings in physics can be traced back to the late 1960s and early 1970s, when physicists began to explore the idea of treating particles as tiny strings, rather than as point-like objects. This idea was initially proposed as a way to address some of the problems with existing models of particle physics, such as the difficulty in reconciling quantum mechanics and general relativity. In the following decades, string theory grew and developed into a rich and complex theoretical framework, with many new insights and predictions about the behavior of particles and physical systems. String theory also gained a large and dedicated community of researchers, who worked to develop and refine the theory and its predictions. In the 1990s, string theory received a major boost in attention and funding when it was discovered that string theory could provide a possible explanation for the existence of dark matter and dark energy, two mysterious substances that make up the majority of the universe's mass-energy content. Despite this excitement, string theory has yet to be confirmed by experimental evidence, and remains a purely theoretical framework. Nevertheless, string theory continues to be an active and vibrant area of research, with many new insights and developments emerging regularly. Overall, the history of strings in physics is a story of a powerful and well-developed theoretical framework that has grown and developed over several decades, and that continues to offer new insights and predictions about the behavior of particles and physical systems. What happens if strings get merged in terms of physics? If strings in physics were to merge, the consequences would depend on the specific details of the merging process. However, in general, the merging of strings could have several implications for our understanding of particle physics and the behavior of physical systems. 1. New particle creation. The merging of strings could result in the creation of new particles, with new and different properties. 1. This could provide new insights into the behavior of particles and physical systems, and could lead to new discoveries and advancements in our understanding of the universe. 2. Increased complexity. The merging of strings could result in a more complex and abstract structure, which could be more difficult to study and understand than individual strings. 2. This could limit our ability to make predictions and understand the implications of the merging process. 3. New theoretical models. The merging of strings could lead to the development of new theoretical models and frameworks for studying particle physics and physical systems. 3. This could result in new insights and advances in our understanding of the universe, and could provide new tools for making predictions about the behavior of particles and physical systems. 4. Changes in properties of existing particles. The merging of strings could result in changes to the properties of existing particles, such as their mass, spin, or other attributes. 4. This could have implications for our understanding of particle physics, and could lead to new discoveries and insights into the behavior of physical systems. Overall, the consequences of the merging of strings in physics would depend on the specific details of the merging process, but in general, the merging of strings could have a profound impact on our understanding of particle physics and the behavior of physical systems. Conclude. In conclusion, strings in physics are a theoretical framework in which particles are modeled as tiny, one-dimensional objects, rather than as point-like objects. The use of strings in physics has many benefits, such as offering new insights into the behavior of particles and physical systems, and providing a possible explanation for the existence of dark matter and dark energy. However, string theory also has several drawbacks, such as a lack of experimental evidence, complexity, and a lack of consensus within the field. The history of strings in physics can be traced back to the late 1960s and early 1970s, when physicists first began exploring the idea of treating particles as strings. Over the following decades, string theory grew and developed into a rich and complex theoretical framework, and gained a large and dedicated community of researchers. Despite the lack of experimental evidence, string theory continues to be an active and vibrant area of research, with many new insights and developments emerging regularly. If strings were to merge in physics, the consequences would depend on the specific details of the merging process. However, in general, the merging of strings could result in new particle creation, increased complexity, new theoretical models, and changes in the properties of existing particles. Overall, the merging of strings could have a profound impact on our understanding of particle physics and the behavior of physical systems. For more videos, stay tuned with us.